Welcome back to the Wednesday evening science session of the conference. Before I introduce the first speaker in this session, I'd like to again remind attendees that you can submit questions for the speaker during and after their presentation by using the Q&A section of the conference webpage. Please do not use the chat section for Q&A. Attendees will not have the option to speak unless the host asks an individual attendee to unmute. Dr. Elizabeth Bach is the ecosystem restoration scientist with the Nature Conservancy based at Nachusa Grasslands in Illinois. In her job, she collaborates with scientists, land managers, and volunteer stewards to investigate questions about tallgrass prairie restoration ecology. Her own research expertise focuses on soil ecology, exploring how below-ground biology supports tallgrass prairie ecosystems through plant-soil interactions and nutrient and carbon cycling. Tonight, Elizabeth will help us to understand the role and dynamics of soil carbon in natural and restored lands.
Thank you so much for the invitation to join you all. I'm Elizabeth Bach, the ecosystem restoration scientist with the Nature Conservancy in Illinois, based at Nachusa Grasslands. Before I get going, I want to thank my coworkers and colleagues who support me and help this research happen. Bill Kleiman, Cody Considine, and Dee Hudson here at Nachusa Grasslands, and all of my colleagues at the Nature Conservancy in Illinois that keep our work moving forward. I also want to give a special shout out to Dee Hudson and Charles Larry, who are two fantastic photographers that do a lot of work here at Nachusa. You're going to see a lot of their photos in this talk, and I like to give them full credit for that. Who finds the concept of soil carbon sequestration intimidating? Well, I'll be honest, I find it intimidating too, and I'm the one who's supposed to be talking about it. So I'm going to invite you all to take a deep breath with me to get going. Okay, well, at least I'm feeling a little bit calmer. Hopefully all of you are as well. The air, the atmosphere, is a really good starting place for a story about soil carbon cycling and storage. What did we all just take a breath of? We know oxygen is what our bodies are using, so that's probably what we're thinking about. But what else comes along with that inhale? 99.9% of our atmosphere is made up of three gases: nitrogen, oxygen, and argon. Now, maybe this is surprising to some of you, maybe not. What's interesting, perhaps, is what's not on this list, and that's carbon dioxide. The current concentration of carbon dioxide in our atmosphere is about 400 parts per million. That's 0.04% of the total atmosphere. So what's the big deal with CO2? Why do we talk about it so much? Well, to bring some of you back to maybe a chemistry class you had in the past, or recent or long term, let's think a little bit about the molecular structure of these gases. Nitrogen in the atmosphere exists as dinitrogen. This is a triple bond holding two nitrogen atoms together. Think about 3 rubber bands between my hands. It's really hard to wibble wobble that, right? It's pretty tight. This is a very strong bond and doesn't react much with other things. Oxygen in the atmosphere exists as O2, a double bond. Again, a little more flexibility, but still pretty hard. And lastly, argon is an inert gas or a noble gas. And this is one of those atoms where its full electron shells are full and it just doesn't react with other atoms very easily. It doesn't really have anywhere for extra energy to go. So when sunlight or solar energy hits these atoms, these molecules, most of it just bounces right back off into space. However, when solar energy hits a molecule like carbon dioxide, where we have 2 oxygen atoms double bound to a central carbon atom, something a little bit different happens. Again, these are fairly stable bonds, but what's happening is these electrons are being shared across all 3 atoms. And when solar energy hits them, they can wobble like a spring, kind of going back and forth. And what happens is it can absorb that solar energy and then contract and release that energy as thermal energy or heat. And that's the source of heat that we're talking about when we talk about a greenhouse gas or warming in our atmosphere. It comes from these molecules like CO2, also methane or nitrous oxide, where there's a lot more give and take, and these bonds can actually absorb solar energy and release thermal energy. But I digress. You all invited me here to talk about prairies and ecosystem restoration, not atmospheric chemistry. So let's all take another breath and refocus. Breathing is the essence of carbon storage and cycling. All living things do it in one form or another. For humans, we breathe in oxygen, it reacts with our food, and that combustion reaction produces the building blocks for muscles, organs, and other tissues. It also produces body heat that keeps us warm. And the byproduct, CO2, we release when we exhale. Now, if only we could engineer a way to reverse that reaction so that we could take CO2 out of the atmosphere, turn it into solid things, and release oxygen back into the atmosphere. Oh, wait, plants. This is exactly what plants do through photosynthesis. They take CO2 out of the atmosphere and using energy from sunlight, convert it into things like leaves and stems and roots and flowers. As a byproduct, they release O2. Bonus points, they're 100% solar powered and have evolved to maximize CO2 capture in almost every ecosystem on Earth. So I could just end this talk here right now. More plants, that's all we need to address climate change, right? Well, like all things in life, it's a little more complicated than that. What kind of plants? There's over 390,000 species of vascular plants on Earth. Which ones where? How does we make this work? We discover about 2,000 new plant species every year. There are plants absorbing CO2 and producing ecosystem functions in ways we don't even know or understand. About 21% of plants worldwide are threatened with extinction. We need to protect the plants we have. They're doing things for us that we don't even realize. And about 5,000 plant species worldwide are considered invasive. They're competing with other plants, impacting things like CO2 cycling, but also crucial ecosystem functions like supporting wildlife and pollinators, as well as clean water and air. So we can amend this core message, right? More plants in the right place. Think about plants that have evolved in their systems and already working to their maximum potential with the other living organisms around them. But wait a minute, isn't this talk supposed to be about soil and carbon? I've just spent almost 8 minutes talking and I haven't even mentioned soil yet. So time for another breath. Did you know that soil breathes too? Snoopy, ever a beacon of wisdom, brings us straight to the heart of the matter. A lot of, we see here is a dead leaf falling off of a tree. And in the last frame, Snoopy's thought bubble says, you don't know it, but your troubles are just beginning. So what troubles does this leaf face? Well, some of you might be thinking it decomposes, and you'd be right. Soil critters, including worms, springtails, fungi, and bacteria, eat those dead plant parts for lunch. They do exactly what we do. Nibble the plant tissue, use it for growth and energy. And although their respiratory systems may not look like ours, they're still using oxygen to produce this process and releasing CO2. Now, it can be really hard to measure respiration from microscopic critters, especially things like single-celled bacteria. So we often measure respiration from soil generally. And generally, soils produce CO2. So if we take a look from a global level, this is a depiction from NASA of the CO2 carbon dioxide concentration in our atmosphere. And this is a snapshot from late July. And what you can see is a lot of blues and yellows. That's a carbon dioxide concentration around 380. And what's really happening on surface here is that all of the ecosystems in the northern hemisphere, these temperate systems, similar to where we live here in the Midwest, are photosynthesizing at their maximum ability. They're taking in CO2 and they're growing a lot. They're producing a lot of plant tissue. And this really pulls CO2 out of the atmosphere. And you can see warmer colors in the southern hemisphere, which would be in the winter dormant phase. And you can see bright spots of red, often around cities where humans are producing a lot of CO2 from activities. If we fast forward to, say, December, when most of the northern hemisphere is now not photosynthesizing and dormant for the winter, we see a different story. And the reason we see such a dramatic shift is because the majority of land on Earth is in the northern hemisphere. So in the winter, we can see these CO2 concentrations spike up into this 390 category, where we see these dark reds and purples. And this is a product of both respiration, decomposition that's happening naturally, and accumulation of human caused CO2 that's not being absorbed through photosynthesis. And again, you can see in the southern hemisphere, we do see a photosynthetic signal in Australia, South America, and Africa, but these land masses are quite small compared to the northern hemisphere. So what this produces is a bit of a temporal way to look at how the Earth breathes. We see an inhale of CO2 in July, and exhale of CO2 in the winter. And typically, this is in balance with our ecosystems. But humans have been shifting this balance. So if we look at where carbon exists on our Earth, the biggest pool of carbon is rocks, stuff like limestone, right? And weathering happens really slowly. Carbon doesn't get emitted from rocks very quickly. It's a very slow process. So this is an incredibly stable pool of carbon, except for fossil fuels that we burn rapidly for energy. And that's the pipeline of carbon from the rock category to the atmosphere, which we see as number 4 on this list. Oceans are the second largest category of CO2, or of carbon, sorry, just carbon. And oceans are actually incredibly effective at buffering CO2 concentrations in our atmosphere. It dissolves passively into ocean water. The downfall is that when CO2 dissolves into ocean water, it creates an acid. It makes the oceans more acidic, and that can have some negative consequences for marine life. So oceans can have some downside to leveraging them as a way to manage CO2 and the heat it produces in our atmosphere. Soil is number 3 on this list. And soil's a pretty big pool of carbon, about twice what we have in the atmosphere. And it also can be incredibly stable. Some of this carbon can hang out in soil for decades or centuries. What's also cool is through plants, as I've kind of hinted at, we can actually move carbon out of the atmosphere and into that soil pool. So how do we do that? Well, decomposition is really the engine driving this. The input, dead plant material, is a product of atmospheric CO2, and that decomposition can result in respiration or can result in some stuff getting stuck in the soil. And the factors that limit decomposition include temperature, oxygen availability, access to plant litter, chemical complexity of plant parts, fire, and human activity. So to get to the root of the issue, soil provides a combination of many of these factors that limit decomposition. The temperature range is more narrow in the soil, and that usually means less decomposition and cooler temperatures. Oxygen has to find a way to infiltrate the soil matrix and is less available than on the surface or exposed to the atmosphere. Litter is often enmeshed in these soil particles. It's harder for organisms to access it and decompose it completely. And also, root plant parts, which are directly inputted into soil, tend to be more chemically complex than some of the above ground plant material. Furthermore, soil can protect organic matter from fire that may combust it on the surface, and can hold onto this carbon for a really long period of time. So all we need is more plants in the right place with less decomposition. World saved, right? Well, there are a few more caveats. So let's all take a breath and get ready to dig in. Soils have a carbon saturation point. Like a glass of water, you can add water up to the brim, but once it hits that point, the water just overflows. Soils have a carbon saturation point. So we can add carbon up to a certain point, but at that point, respiration balances inputs and you're not really getting any net accrual of carbon. You're just keeping it. So the two key messages here are places where our soil carbon glasses are full, we want to keep them full. Places where the soil carbon glass isn't full is an opportunity to fill that up. And to break this down, I'm going to share some data from 3 different research projects. On the far left here, we have a project from Northern Illinois on a clay soil prairie restorations at the Fermilab site. And some of you may be familiar with that site, others not, it's okay. These are prairie restorations. And what Matamala and colleagues did was look at soil carbon concentration in these restorations, ranging from a few years old to several decades old, and then compared it to native prairie remnants, which had never undergone human land use conversion to row crop agriculture. And you can see a pretty dramatic difference between these. The middle frame is from a study I was involved in Nebraska, again, looking at prairie restorations and remnant prairie. Pretty decent distance there. And then the furthest one on the right is some work done at Nechusa several years ago, again, looking at soil carbon accrual in restorations. And we can see that increase over time, over 20, 25 years. And for a variety of reasons, we weren't able to do a comparison with remnant soil carbon at Nechusa. But the points I want to make here are that this actually demonstrates the different size of glass or cup that these soils represent. I've added gold stars to these y-axes, and the gold star represents the exact same value. So you can see the scale isn't exactly the same. And what we see in these clay-rich soils from Northern Illinois, that gold star is quite a bit lower on the y-axis, meaning that these soils have the ability to retain a lot more carbon. Whereas in the drier Nebraska soils and the sandier Nechusa soils, we see those gold stars compared to the study sites at a higher level. And this basically breaks down to the difference between a 32-ounce big gulp in these Fermilab soils and an 8-ounce coffee cup in these Nebraska or Nechusa soils. And there's nothing wrong with that. It's just what they are. It's their inherent property. And if we take this to think about how do we fill these glasses up, what we can see is that in these clay-rich Illinois soils, we have a lot more cup we can fill up. We've got 32 ounces. We're starting down here. We can put a lot of carbon or liquid into this cup, but it's going to take a long time. That rate of accrual is pretty similar. In this study, they estimated to take about 300 years for a restoration to accrue the carbon that a remnant native prairie has. In the Nebraska study, we estimated about 150 years. And this is a smaller carbon cup. You can see the distance, the magnitude of that difference between the remnants and the restorations is a little bit smaller. So it just takes less time to fill that cup back up. So there are 3 steps protecting carbon in soils. The first is accrual, which is what we were just talking about. How does carbon get into the soil and accrue there and stay there? The second step is storage, and this has to do with the pool, the size of that cup, and how much carbon can actually end up in that soil. And then the third step, kind of the holy grail, is sequestration. And the difference is sequestration really has to include a measurement of what we would call permanence, or how long is that carbon going to stay in the soil. When conditions change, things like warming temperatures or increased precipitation, that carbon saturation point can actually shift in a soil. And so as we're actually feeling effects of climate change, we have to recognize some of our soils may be responding by respiring more and actually losing carbon. So we have to really think about that time element and how these soils are holding on to carbon for the long haul. So I'm going to build us back up and leave us with a few action items to feel like we can really make a difference. And my key recommendations are protect what we have and restore where practical. So to break this down, we're going to get some advice from the far side, always a great place to look. And what we see here is the adult in this comic telling the young person, and you see this ring right here, Jimmy? That's another time when this old fellow miraculously survived some big forest fire. So the point here is protect what we have, right? Trees that have survived environmental disasters, we should leave them standing instead of just cutting them down. And in a state like Illinois, where I live, we can see a pretty dramatic transformation of our landscape in the past 150, 170 years. A landscape that was dominated by grasslands, forests, and wetlands is now today dominated by intensive row crop agriculture and urban areas. And it's really important to protect what we still have in this region and in this state. These soils that have undergone conversion in land use have lost about 30 to 50% of their carbon. They're now glasses half full. And these places where that have been protected from conversion, those are glasses that are already full. And a key action is to keep those full glasses full. So this is some work some colleagues of mine at the Nature Conservancy did a couple of years ago. And I do want to caveat, this is a global analysis. These numbers would not necessarily map down to our local areas in the same way. So, keep that in mind. This isn't an absolute. It's more about showing some potential here. And here we have avoided grassland conversion. These are our full glasses of grassland soil carbon, and keeping them full is actually a really important contribution to climate mitigation globally. Now, here in the Midwest, we don't have a lot to protect, right? So restoring where practical becomes another important tool in this toolbox. And if we come back to this image, we see grassland restoration sorting out a little bit lower in its potential for climate mitigation. But it's also important to remember that climate mitigation isn't the be-all and end-all of ecosystem restoration or the work that can be done to protect nature. So there's other benefits that come from protecting grasslands and restoring grasslands. And that includes things like biodiversity, protecting rare and declining species, protecting water quality and air quality in our communities where we live. And restoration and protection is critical to all of those co-benefits. And in fact, ecosystem restoration, I think, is one of our bigger bangs for our buck, in that these approaches not only contribute to mitigating climate change, and believe me, we need everyone on board to address climate change. It's a huge problem, but we also gain these additional benefits from biodiversity that also needs a lot of help, and making healthier communities for all of us to live in. So for all the overachievers out there, I really have 5 take-home points from this talk. More plants in the right place with less decomposition, by protecting what we have and restoring where practical. I look forward to continuing discussion and questions in the Q&A session. Thank you.